Okay, so so at the end of last Tuesday, we consider superposition of the eigenfunction U sub n. Okay, and now so this function satisfies the Peirce equations. Okay, and the three homogeneous boundary conditions. And provided that the series converges. Okay, and the series of termwise partial derivatives converges to the corresponding converge to the corresponding partial derivatives. Of the sum okay. Now by the inhomogeneous boundary condition on the top edge of the plate, we have f of x is equal to u of xb. Okay. So that is star sine a pi x hypersine pi b of a. Okay, and so this becomes to be a star sine hypersine pi b divided by a, and the sine pi x a. Okay, for all x in Z and A. Okay, so this is the inhomogeneous boundary conditions. And you can see that which is the Fourier sine series expansion of f x 0 to a. Okay. All right. Now, let's we have that an star hypersine pi b divided by a is equal to 2 of a integrate f of 0 to a f of x sine pi x a and the dx. So the AN star. So AN star becomes 2 A hypersine n pi b divided by A into 2 Okay, so finally fxy the u equal to okay, and so I think we will use u du here, and the sine n pi x divided by A, and the hypersine n pi y divided by A. Right, so now we find a solution, okay, which is satisfied the Laplace equation as well as the 4 boundary conditions, the 4 edges of the rectangular plate, respectively. So, any questions? So which satisfy the Laplace equation as well as the Dirichlet boundary conditions. Okay. Now the next section, we will consider heat equations. For a volume bar. Alright, so we consider so the x spatial variable we extended on both sides to infinity. Okay, so we assume that the bar of a bar which extend to infinity on both sides. And is natural insulated. And in this case, we do not have any boundary conditions. But only one initial condition. Okay, and so the initial condition will be u of x0 equal to f of x, and for x from minus infinity to infinity. So this equation will be called 12.7.1, and the boundary condition will be 12.7.2. Alright, and so f of x is the given initial temperature of the bar. Okay, and is in general non-periodic. Okay, so this can be an arbitrary temperature function. Okay. So again, to solve the one-dimensional equation together with the initial condition, so we will first again use the method of separating variables. Okay, so technique. So we let u of x t to be f of x and g of t here. Okay, and so where f of x is the function of x in the whole line, and gt is a function of t in the y. So as we have when we discussed in the previous section, okay, so this gives two ODEs. So we just redundant it, f minus kf equal to 0, and then g prime minus k c square g equal to 0. So the first one is a second order ODE, and the second one is the first order. Okay. Now, for k, so now there are three cases. Case 1, k equal to p square, which is positive, with p with z, a general solution. Okay. So this is called trapezoid. So general solution of the first ODE in the previous equation. Right, so we sub them. The f of x is equal to a e px plus b e minus px here. Alright. Now if a is not equal to 0, okay, then so if a is not equal to 0, then the absolute value of x will goes to infinity, okay, as x goes to infinity. Right? Okay, so if this is not 0, now if x goes to infinity, because p is positive, so we have exponential growth, so that the absolute value of x will goes to infinity. Okay, and we know which is physically, so that which has no physical meaning. Yep. Let's say which has no physical meaning. Okay. And similarly, if b not equal to 0, then f of x again goes to infinity as x goes to minus infinity. Okay. So if b is not 0, when x goes to minus infinity, this term goes to infinity. Okay. Okay. So again, which has no physical meaning. 2. Thus, we have a equal to b equal to 0, and okay. And f of x is equal to 0, which implies that u of xt is equal to 0. A trivial solution. Okay, so we see. Now, case 2. Okay, 0. So a general solution. Okay, so a general solution of the two ODEs are here. F of x is equal to ax plus b, and gt equal to c here. Now if a not equal to 0, then f of x goes to infinity as x goes to minus plus infinity, which has no visual meaning again. Alright, so that's a is equal to 0, and and the U, xt. Okay, and we used a parameter, so it's 0 here, corresponding to case with 0. Alright, so we have B times C. So this is a constant solution of the heat equation. Okay, so it's a constant solution. So of course the constant solution of course satisfies the heat equation. Okay, because when it's constant, then this is 0 equal to 0. Okay. We haven't applied the initial condition yet, but we just say here, just consider the one-dimensional heat equation. Now case 3, is minus p square, so is negative. Now the two ODEs becomes 2. Alright, so it's f the prime plus p square f equals 0 for x in R, and g prime plus c square p square, and the g equal to 0 for all t greater than 0. So that, and their general solutions. Okay, or so the general solution are here. F x with the parameter p here, and which would be a1 of p cosine px plus b1 of p sine px, and for x in R. I forgot. For all x in R. Alright. So this is the general solution we have. Okay. And the G, T, P, x C of P square p square t for all t equal to 0. Okay. Any questions? And we for the coefficient here, with regard to coefficient as the function of the parameter, because later on we will use them. Okay, so just write them down. That's okay. So here, maybe I will say A1 P, B1 P, and CP arbitrary and dependent only on the parameter P. So now basic variable. So in summary, UX T P equal to AP. AP cosine PX plus BP sin PX exponential minus C square P square T for all x in R and P equal to 0. Okay. So now is a solution of the one-dimensional equation. Okay, and called the eigen functions corresponding to the eigenvalue known dot P, which is equal to Cp for all P equal to 0 here. So we include P equals 0, because when P equals 0, so we see that it's a constant, right? And so it's 0, then this is 0, this is 1, this is 1, and so that is A0 is a constant. Okay. Okay. And we regard the eigenvalue to be C times P. Okay. Now, since, but as you can see that for any of this parameter P, this is a solution of the equation, but when you consider the initial condition, consider the initial condition here, right? You can see that the initial condition may not satisfy for any of this function for any particular P. Okay, because when you try to, you see that, so when P is 0, so you see this is A of P, but when this is 1, so you have P cosine Px plus P of P sin Px. Okay, and which may not equal to f of x, right? In general, except that the initial condition of x is equal to, okay, it's just equal to this function. Right? It's exactly, okay. So in general, this is not true, okay. Except f of x is selected to be such a linear combination. So this is generally not equal. But since the heat equation is linear and homogeneous, okay, so any superposition of the eigenfunctions of the heat equation is also a solution of the heat equation. Now, but since the spectrum lambda p equal to 0 is continuous, alright, so any superposition of the eigenfunctions will be represented by an integral. Okay, and so the integral right here will be, so u of t, so we'll consider rho 0 to infinity because the whole spectrum, and u of x, t, p, and dp. Okay, so the integral over the parameters p. Our spectrum is just the proportional to the parameter. Okay. All right, and so that you have for a of p and cosine px plus bp sine px together x minus c squared p squared t and the dp for all x in R and the t equal to 0. Okay, so we call this chart 7.4. Alright, so this one must be our solution. Okay, and so we will show that the integral in the previous equation is indeed a solution of the heat equation in chapter 0.7.1. Okay. Provided that A of P, B of P, P square A of P, and P square B of P are absolutely integrable over the interval from 0 to infinity. Okay. Okay, so we will show that the integral. Yeah. Okay, and so we have to use the theorem in chapter 11 about differentiation under an integral sign. Okay, so we now use theorem EE202001, which is the differentiation under the integral sign. Alright, to show that, so we want to show that okay, so we use to show the above, to show that the integral is indeed satisfy the equation. Okay, now okay, so now since so we have assume, so now we assume that okay, AP, B of P, and P square of P and P square B of P are absolutely integrable. OP. So now since P of AP less than AP for all P in between 1 and 1, and P of AP absolute value is equal to P square A of P, okay, for all P greater than 1. Okay. So we have that if we integrate P of AP here, so this is this equal to AP plus P square so this is implies that PAP is equal to AP plus P square AP for all P greater than 0. Okay. So we have that. Means that P of AP is absolutely integrable over 0 to infinity. And similarly, P of BP is also absolutely integrable over 0 to infinity. Okay, so AP, BP, P squared times AP, and the P squared times BP are absolutely integrable, implies that P times B or P and A times AP are also absolutely integrable. Okay, similar. Okay, so we have this result. Okay, now we first fix an x in R, and we regard u of x t p, okay, as a function of p and t. Okay, so because u x t p x are special variables from minus infinity to infinity. T is the temporal variables starting at 0, and the p is our parameters also going to 0. Okay, and now we first fix an x, so now u can be regarded as function of p and t. Okay, on this Cartesian product here. Okay. Now we have the correspondence x with p and y with t here. Okay. So if we have the note of theorem 11.7.b at hand, okay, then we can see how to apply the theorem. Okay, and in that theorem we have consider f of x, y, right? And now the correspondence is that u of x and the t, p, okay, here this is a of p, cosine px plus bp sine px, and now the x is fixed, so this is a constant, okay, this is constant, so it's a superposition of A of P and B of P, right? So the superposition of the two functions of P times a function of P and X. Remember here, this is a function of P and T, okay, P and T there. And the partial derivative with y corresponding to the partial derivative with respect to t here, okay, to t. And so we will take t so that we have only this one, and now we have minus c square, p square, and ap cosine p. Oh, I'm sorry, it's not constant because it's a function of p, okay. Okay, so this is not constant, I'm sorry, but yep. So it's a sum of two functions p the product to function p and the product to function p. I'm sorry, this is not constant. Okay. Even though x is constant, but it's a function p. Okay. So this is here and bp sine px, and we have minus p squared t. Okay, so we have this one. Now and noting that, because in theorem 11.71b, we have to know that first of all, the function of p and t, because we regard this one as a function of p and t. Alright, and so this is AP cosine px plus BP sine px okay, it's absolutely integrable over p in 0 to infinity okay, for each given t greater than equal to 0. Okay, because when we form here, we actually integral over p. Okay, we integral over p there. Okay. Alright, so as you can see that for each t, okay, for each t here, t greater than equal to 0. So this is the integral over p, and we know it is. So this function. So if p is fixed, we already fixed x already, right? Now if p is given, so p is fixed, then this is equal to a function p. And we see that as a function of p, this is absolutely integrable. Okay. The reason is that if we take the absolute value, we find that this is less than equal to AP plus BP. Why? Because the exponential term is less than equal to 1. Okay? The biggest value is when t is 0, which is equal to 1, otherwise it will exponential decay. And the cosine sine function has absolute value less than equal to 1. Okay? So that the absolute value of u is the sum of the absolute value of a and the b here. And we know both AP and BP are absolutely integrable. Okay. Over P in 0 to infinity. Okay, so first of all, that we really can do the integration. So for each t, and for given x, right? Okay, so if x is given, t is given, then this integral exists. Why? Because that as a function of p, this function is absolutely integrable over dp. So we really can evaluate this integral. Okay, so this function it just says that this function is well defined. Okay, you can do the integration. Alright, so you can say that this says that u of xt is well defined. 7.4. Okay, the second, the partial derivative with respect to, as we have shown the partial derivative here. Okay, so this minus and p square AP cosine px plus bp minus c square p square t exists for each interior point pt of 0 to infinity cos 0 to infinity. Okay, because this region has a boundary. Okay, but in the interior point, these partial derivatives always exist. And third one, as you can see, the partial derivative with respect to t, okay, is less than or equal to a function of p. Okay, defined to be c square p square the reason is that this term is less than or equal to 1, and the cosine, and the sine here, cosine sine has absolute value less than or equal to 1. So the partial derivative is less than or equal to h of p here, and this h of p for each interior point pt of 0 to infinity, and h of p is absolutely integrable over p is in 0 to infinity. Okay, why? Because we have assumed that p square AP and p square BP are absolutely integrable. So we know that they are absolutely integrable. Okay, so we have 1 and 2 and 3. So these 3 conditions are required for the conclusion of theorem 11.7.b to be true, right? And what is the conclusion? Then we can do the differentiation and the integral sign. Okay, so now we have that. The conclusion is that the partial derivative, is absolutely integrable over p for each t 0 and in this function, this one has a partial derivative. Okay, so this partial derivative exists for all t equals 0 with okay. So now when we do the partial derivative with respect to t, okay. Okay. We can exchange the order of differentiation and integration. And this is y square, p square, ap, and cosine px plus bp, sin px, e minus c square, p square t, and dp. Okay. Okay. Alright, so this is this partial derivative appears in the left-hand side of the heat equation. Now, but the right-hand side of the heat equation makes the second-order partial derivative of u of x, right, with respect to x. Okay, so we have to do the similar. So we have to check. We have to check the similar thing, and alright. So with similar argument, please see the details in the lecture notes. Okay, so I will dispute the lecture notes for you. Okay, so we have that so that exist, okay, for all x in R, and okay, so you can find that this is plus b p sin px dp. Okay. Now you compare, if we multiply c square here, so we have c square. Okay, and you look at these two, minus c square, integration, p square here, and the summation and the exponential term in dp. Okay, so you conclude that is equal to c square is satisfied. So this integral is E of xt satisfies the heat equation. Okay. So which proves that the U of xt in 12.7.4 is a solution of the heat equation. Okay, provided that and you see that the A of P, B of P, these two functions are arbitrary. They are arbitrary here, right? Provided that, but let's say the A of P, B of P, and P square A of P, and P square B of P, okay, are absolutely integrable over 0 to infinity. This is the only requirement. Otherwise, the A of P and B of P can be arbitrary. Okay, so you can put into arbitrary a function of P. Okay, it can be arbitrary, and B function of P there. Okay, so that this integral, which define the function of x of P, and this function will satisfy the heat equation. Okay. So you may think of it as this is a general solution, right? Because A of P and B of P can be arbitrary. Okay, so this is a general solution for the heat equation. Okay. Any questions? Now we have an initial condition to be satisfied. So now we next determine A of P and B of P from the initial condition. In 12.7.2. So now f of x is equal to u of x 0, and this is become to AP cosine px plus bp sine px and the dp. And when we look at this one, which is just the full integral representation we discussed in chapter 11. Over the x, and it's valid is, so AP can be obtained 1 over pi from minus infinity to infinity f of x cosine p of x dx. And BP is 1 over pi minus infinity to infinity f of x sine px dx for all p greater than or equal to 0. Right? If f of x is continuous and absolutely integrable over the continuity is because we want the representation becomes to be exact. Otherwise, the representation becomes to what? It becomes to the average of the left limit and right limit at every point. Okay. But if the f of x is continuous, this is quite often, okay, and physically, that the temperature of an infinite long bar, okay, has the temperature which is continuous over on x, okay. So this is quite physically reasonable to have, okay. So if f of x is continuous and absolutely integrable, then we have the full integral representation because we have full integral theorem in chapter 11 there, okay. Alright, so we want f is continuous, and also we also ask the f of x has the right hand derivative and then the left hand derivative at every point in R by a Fourier integral theorem. i.e. theorem 11.7.1. Okay, so let's see. This is 12.7.5, and this is 12.6 here. All right, so the Fourier integral theorem tells us that this is true. This two equation, and if f of x is continuous and absolutely integrable, and has the right hand derivative and the left hand derivative there. Okay, but So furthermore, right, we'll show that we'll next show that 0.7.5, so this boundary condition together with 12.7.6 is valid if f is continuous on R and both f of x and both f of x and its Fourier transform FAP are absolutely integrable over R. Okay. Right. So this is another condition for these two equations. So the identity in these two lines here are valid. Okay. Okay. So this condition is from the Fourier integral theorems. Okay, we have. But another thing is that we don't need to worry about the right-hand derivative and left-hand derivative of f of x. Okay, that you just check whether f of x is absolutely integrable, and we know if f of x is absolutely integrable, then it has Fourier transform. Now, so now we next check that whether the Fourier transform f a is also absolutely integrable. Okay. All right, and so by theorem, 11.9.b we have here. Right. So if FAP is also absolutely integrable, then we know that we can recover, and then we also know f of x is continuous already. So we have for this one. So we have the inverse Fourier transform. Okay. So now we have the Fourier transform. Okay. Remember, the Fourier transform is a function of p, and p is from minus infinity to infinity. It's not like the Fourier integral theorem that the a and the b are a function of p, which p is greater than or equal to 0. Okay, so we consider only positive frequencies. Okay, but for Fourier transform, we consider frequency which can be negative and positive. Okay, so they are different. So now we have, since f of p, ei p of x, right, so that the integral here, so we know that this is by definition of the Fourier transform. So this is the f of v and the EIPV. Okay, so this is FA. FA is just the integral, but we multiply with so this is dv times EIPX. Okay, and so you can see that f of v and the face becomes 2 x minus v here. Okay, so you can see this is a convolution, convolution of this function and this function. Okay. So now and now by Euler's formula, we have FV and the cosine P of x minus V dV plus I 1 over square root of 2 pi f of V sine P of x minus V dV here. Okay, so this is called 12.7.7. Now, we see here this one, an even function of P, okay, because we have cosine here, so if P change the sign, then because cosine is even, so there is no effect. But because sine is odd function, so this integral is also an odd function of P. Okay, and so now, so the identity in 12.7.7 here becomes to here. So f of x now is equal to 1 over root with and 1 over 2 pi. Okay, f of v cosine p x minus v and dv and the p here. Okay, because the imaginary part is 0 because it's an odd function of p. So when you integrate over p, this function, the integration of this function of p is 0. Okay. And again, because it's, this is an even function of p, so the integration becomes 2. So you can see this is 1 over pi, and you can integrate from 0 to infinity, and minus infinity to infinity, fu, and cosine p, x minus v, then the dv, dp. Okay, for all x in R. Okay, all right. So this procedure, if you recall the procedure we derived for integral, right? The Fourier transform. What we have done here up to now is the reverse process. Okay, is the reverse procedure that we derived the Fourier transform. Okay, and then now we expand. Now we expand. So we have v, and so this is cosine px, and cosine pv plus sine px sine pv. and dV dP. Okay. Alright, and so now so we will have 1 over pi f over v cosine pv and dv, okay, cosine px plus 1 over pi fv sine pv dv sine px and dp. Okay, and that you have, this is called AP cosine px plus bp sine px and dp. And here AP equal to okay. Alright, so with the assumption that f of x and its Fourier transform f hat of p are absolutely integrable, then of course that then these two, then the identities in these two lines will be valid. Okay. Any questions? Okay, so now we find the A of P and B of P, right, according to our initial condition, the initial temperature here. Okay. Now, so now the further, now substituting A at P and B at P in 12.7.6, okay, into 12.7.4, okay. Where we define U of xt, right? So now the solution the solution becomes to plus 1 over pi sine px. Okay. Exponential minus c squared p squared t and dp. Okay, now 1 over pi is here, equals 0, and we have from minus infinity to infinity, and the f of v, and cosine pv cosine px plus sine pv sine px, okay, and dv here, okay, great. Exponential pp, okay, so we just move here, move to here, okay. And so this is becomes to the cosine p of x minus v here, okay, so this one, okay, so now we can express the solution which satisfy the heat equation as well as the initial condition. So now u of xt becomes to 1 over pi 0 to infinity, and from minus infinity to infinity, f of v cosine p x minus v dv here, and e minus c square p square t and dp. Okay, and you exchange the order of integration. So we have fv here, and e minus t cosine p x minus v, okay, and dp first and dv. Okay. And this is by Fourier theorem. Okay, because we can evaluate the one order, this order of integration, then you can exchange the order. And so the inner integral can be evaluated by the following formula. to infinity e to minus x square, and cosine to b s and ds, okay, is equal to square root pi over 2 times exponential minus b square. Okay, so this is the identity of this kind. This is a special kind of integral. Okay. So that by letting s is equal to c square root t times p here, right? So we have cp square root of t here. So we have that u of xt, okay, becomes 2 minus f of v and 1 over 2c square root of pi t. Okay, and the exponential that minus x minus v divided by 2c square root of t and square and dv. Okay, so by the curve here, okay, so this is just by, you can compare that x is the cp square root of p, alright, and when x is cp square root of p, then you can see what is b, right? You can see so okay, so that you can see 2bx, x has been times cp square root of t, and 2bx is equal to p of x minus, you cancel p there. So you see that b is equal to 2c square root of t, 2c square root of gx minus v here. So b is this one. Okay. Okay, and as you can do the change of variable, so that z is equal to v minus x and 2c square root of t here. Then this integral becomes to infinity minus infinity f of x plus 2c z square root of t and 1 over square root of pi and e minus z square and dz. Okay. Okay, and here it can be shown that if f of x is f of x is bounded, okay, for all x in R. So if f is bounded, which means that f of x is equal to m for x in R for some n greater than equal to 0. Okay, so if f is a bounded function, okay, and integrable in every finite interval, and so if f of x is bounded and is integrable in every finite interval, okay, then the function okay, so the functions in the u of xt, so let me see, okay, point 6, 7, 8. Okay, so the function in, okay, satisfy the heat equation and the initial condition. Okay, so this is very general. Okay, this is a very general. Why? It is more general than the previous result, because if in the previous results we either ask for the initial temperature f of x is either continuous. For example, we ask for f of x is continuous and absolutely integrable, and its Fourier transform is also absolutely integrable. Then in this case, then the u of x, okay, u of x we obtained in the equation 12 plus 7.4 satisfy the equation as well as the initial condition. Okay. But in here it's more general because the temperature f of x we just ask for is bounded. Okay, it's bounded. And it's integrable for every finite interval. Okay. Such a function may not be absolutely integrable. Why? For example, if f of x is a constant function, a constant equal to 1. Constant function is not absolutely integrable over the whole real line because the integral is infinite. Okay? It's infinite. Even though it's continuous, but it's not absolutely integrable. But it fits through here, it's bounded. And if we integrate a constant function over a finite interval, you get a number, right? So it's integrable. So constant function is good, okay? And so if we put a constant function C here, you get a solution, okay? So you have a solution there, okay? And this is corresponding to the so-called normal distribution. Is about it's a kernel of normal distribution. Okay. Yeah, I think you are only so next semester you will take probability course, right? And then you will be familiar with the normal distribution then. Okay. So this is related to the probability density function of the normal distribution. Okay. I believe you learn normal distribution in high school, especially in the third year, right? In the third year, when you consider random variables, you start random variables, then I think that would be the last semester in high school. I believe that because recently I have a chance to take a look at the textbook of high school mathematics, and I'm amazed because you learn a lot of statistics and the probability and the combinatorics, and also you learn calculus there. You know how to find the limit of sequence, how to find limit of series, and you know how to find the limit of function, and you know how to do the integration and the differentiation. A lot of things. These things we didn't learn when I was a high school student many years ago. Okay, so you actually learn a lot than me. Okay. I'm surprised, yes. Yeah, because I didn't know that before I took a look at the textbook of the high school mathematics. Okay, so this is a very general expression of solutions, and this will embed the initial condition into the solution. So the initial temperature f of x has been involved in the solution directly here. So this is an amazing solution here. Okay, but the proof of this general form needs some work. So I will give you the reference to find how that the proof, if you are interested in that why under this condition of the f of x that the integral is provided here satisfies the equation as well as the initial conditions. Okay. Okay, and I think I left a topic that the topic is that how to use Fourier transform and Fourier cosine sine transform to solve the heat equation directly. Okay, right. So I will distribute the lecture notes for you to read. Right. Okay. So I think I stop here.